This video covers Chapter 10, which introduces randomization distributions and p-values. So first of all, what is a p-value? A p-value is a way of measuring how strong the evidence is against the null hypothesis. Technically speaking, what it measures is the chance of observing the sample data, or data that more supports the alternative hypothesis, by chance if the null hypothesis is true. If the p-value is small, then the sample data are inconsistent with the null hypothesis. They would be unlikely to occur if the null hypothesis were true. So the fact that they did occur makes them inconsistent with the null hypothesis. And there's strong evidence supporting the alternative hypothesis. When we're using the p-value to think about how strong the evidence is, the smaller the p-value, the stronger the evidence is against the null and in support of the alternative. And what we consider sort of small is very small in statistics for this sort of measure of evidence. So something down below 0.01 would be considered very strong evidence against the null hypothesis. Anything above 0.10 would be weak evidence against the null hypothesis, and everything else is sort of falls in this shades of gray in between. So when we want to find the p-value, the way that we are going to use to do that is a randomization test. A randomization test uses a null model to simulate a distribution that shows sample statistics that might occur due to random chance if the null hypothesis were true. The simulated distribution is called a randomization distribution, and that's where this type of test gets its name. An example, we looked at the XSort procedure last week, and we saw that if we wanted to find out if there's strong evidence that people who use XSort are more likely to have girls compared to the general population, our null hypothesis was that XSort does not change the chance that a person will have a girl, that they would have a 49% chance, just like in the general population. And the alternative hypothesis, remember, was that XSort does make people more likely to have girls, that they would have a more than 49% chance of having a girl if they use the XSort procedure. A study was done to evaluate how well this XSort procedure worked. And what they found is that 879 out of 945 people who used the XSort procedure gave birth to girls. The randomization distribution we're going to simulate to show what the distribution of sample proportions look like for samples of the same size, n equals 945, if every woman in the population had a 49% chance of having a girl. So what kind of statistics might happen by chance if the null hypothesis is true? And we're going to simulate this distribution using STAT051, and we'll walk through the steps. So first of all, when we want to create a randomization distribution, we go to the randomization hypothesis test area over here in STAT051. We choose a test for single proportion here because our hypotheses are about the proportion of births that will result in girls using the XSort procedure. Once we come into the randomization test for proportion applet, we're going to need to start by editing the data so that we can have the data from our original sample in STAT051. When we edit the data, we put in the values from our sample. There were a count of 879 girls out of a sample size of 945 births. We click OK. And then we see the data from our original sample are in the upper corner here. And now we need to make sure that the proportion that we're simulating our results around match our null hypothesis. Now this is almost our null hypothesis, but not quite. Remember, our null hypothesis is that the proportion who would have girls using expert is 49%. So I'm going to click on this blue box with a 0.05 in it, and I'm going to change the null hypothesis proportion to 0.49, 49%, and click OK again. Once I do that, I generate 1,000 samples and get this distribution. So this is our randomization distribution. Notice that it's centered around the null hypothesis because the whole purpose is to show us the kinds of sample proportions we might expect if 49% of people who use this expert procedure end up having baby girls. So if there's a 49% chance of having a girl, we'd think that most of the time we'd get a sample proportion that's close to 49%. Sometimes just by chance we're going to get a few extra girls, more than we were expecting. Sometimes we're going to get a few extra boys. And once in a while we'll get a result that's really far away from 49% just due to random chance. Right? So this is allowing us to see what kinds of sample proportions would be consistent with the null hypothesis, the ones that would be sort of likely to occur, and what kind of sample proportions would be inconsistent with the null hypothesis, ones that would be very unlikely to occur. Now remember, the p-value is the chance of observing the sample data or data that's more extreme in support of the alternative hypothesis by chance if the null hypothesis is true. So how are we going to find that? First of all, we use the alternative hypothesis to decide if we are going to use a right tail or a left tail on our test. When our alternative hypothesis is a more than statement, we use the right tail because the larger values in the distribution are going to be the ones that are more supporting the alternative hypothesis. If our alternative hypothesis is a less than statement, then we use the left tail because it's small values that are going to support a less than alternative hypothesis. So once I've decided which tail I want, I click the appropriate tail and stat key. For the export, that's the right tail. So we click this box here, and it puts a right tail on. Now what it's going to do is it automatically will put 0.025 in the tail and show us the value that cuts that off. But remember, this is not our p-value. And the reason that it's not going to be our p-value is because the p-value is the chance of seeing our original sample proportion or something more extreme in this distribution. And this is not our sample statistic. In order to find the p-value, I want to start the tail at the observed sample proportion from the original sample. So I need to start the tail here at 0.93. So to do that, I'm going to click on this box and I'm going to change this value to 0.93, which I'm getting from the original sample, remember. Once I do that, stat key will calculate the proportion of dots in the appropriate tail beyond our sample statistic, and that is going to be our p-value. So we can see that there were no dots out at 0.93 or beyond. There are 0 dots in the tail. We divide the number of dots in the tail by the number of samples generated, So that's giving us 0, which is our p-value. Now we're thinking about how strong the evidence is against the null hypothesis. Our p-value is 0. So the evidence is very, very strong. With a p-value of 0, we conclude there's very strong evidence that those using XORT are more likely to have girls. Next, I want to talk a little bit about what it means for something to be statistically significant. To determine whether something's statistically significant, we use a threshold called the significance level to make a formal decision to either reject the null hypothesis if the p-value is less than the significance level. This would mean that there's statistically significant evidence against the null and in favor of the alternative hypothesis. Or we might decide that we fail to reject the null hypothesis, and we would do that if the p-value is greater than or equal to the significance level. This would mean that there's not statistically significant evidence in favor of the alternative hypothesis. Most researchers use a 5% or 0.05 significance level. It's almost universally used. So looking at our XORT example again, we had our p-value of 0.000, right? Since this is less than 0.05, we'd reject the null hypothesis, and we could say that there is statistically significant evidence that those using XORT are more likely to have girls. Let's look at another example. There is also a Y-sort procedure, which is intended to increase the chance that a person will have a baby boy. So our null hypothesis, if we want to check to see if Y-sort works, is that Y-sort does not change the chance that a person will have a boy, and that it's 51%, versus an alternative that those using Y-sort are more likely to have boys. They have more than a 51% chance of having a boy. In this case, a sample of 152 people tried the Y-sort procedure, and 84 of them had boys. Looking at the output from STAT051, we can see a couple of things. First of all, we can see that the original sample proportion here was 0.553. That's our observed result. We can also see that we needed to generate a randomization distribution centered around the null hypothesis, that the proportion having boys with Y-sort would be 0.51. And because we were testing to see if people were more likely to have boys, we used a right tail and started it at the sample statistic. The proportion of the simulated results that were in this tail is 0.136. This is our p-value for this test. So how strong is the evidence against the null and supporting the alternative? Well, our p-value of 0.136 falls into the weak range. So this p-value is weak evidence in favor of the alternative hypothesis. The p-value is more than that 5% level of significance, so we don't reject the null hypothesis. And in this case, we'd say that there's not statistically significant evidence that those using Y-sort are more likely to have boys. One thing to just be careful about is to remember that when we fail to reject the null hypothesis, this does not mean that the null hypothesis is necessarily true. It means that based on the sample, the evidence in favor of the alternative hypothesis is not statistically significant. And we'll talk about this more in a later chapter when we talk about some of the sort of cautions related to hypothesis testing. Last thing I want to just talk about quickly is just to remind us of what the difference is between a bootstrap distribution and a randomization distribution. A bootstrap distribution is used when we're making a confidence interval because it's created by resampling the original sample data. It ends up centered near the point estimate from the original sample. A randomization distribution is used for hypothesis testing because it's simulated to show results that are consistent with the null hypothesis. It will always end up centered near the null hypothesis. And the whole purpose for simulating that randomization distribution is to show a distribution of statistics that might occur by chance if the null hypothesis is true, so that we can then find the p-value.